Jim Puckett. He's a professor of geoscience and education chair at the Boone Pickens School of Geology at Oklahoma State University. He specializes in physical stratigraphy, and geology. Prior to joining the faculty in 2000, Dr. Puckett was an exploration geologist working mostly in the northern and central Oklahoma regions, the DJ Basin, the Colorado, and eastern shelf of the Midland Basin. He is presently involved in studies of the conventional and unconventional reservoir, including the Hunton Group, the Caney Shale, Woodford Shale, and Pennsylvania Sandstone and Marbles. He is also involved in a research project concerning the characterization of aquifers and improving STEM education. In addition to his collegiate instruction research, Jim is active in outreach, including teaching, training, several workshops for secondary school students, and presentations to school and youth groups. He thrives on field work and directed the OSU Les Houston field camp near Canton City, Colorado for more than 20 years. Please welcome Dr. Puckett.
Thank you very much. It's always good to be back up here and attending one of the summits. And as a former exploration geologist and one who will admit right up front that I've caused a lot of dry holes to be drilled, I'm always looking at geology from exploring for oil and gas, or as we say now, managing fluids in the subsurface. So we're looking to map the subsurface, figure out how to get fluids out of the subsurface, whether it's gas or oil. And now we're, as Nick showed us so well, we're looking at all these reservoirs as potential repositories to store whatever we want to store in them. We talk about storing CO2. I like to always add that U, carbon capture utilization. Let's get some more oil out, that CO2, which they're doing successfully here at Burbank. But you're going to see subsurface geology. I did not put any outcrop slides in. I probably should have, because we have some great outcrops that go with some of these rocks. So what I'm going to talk about today in very generalized terms are three areas, including two that are not in Osage County. Now, Cleveland Field, I admit it's on the river in Pawnee County, but I'm going to talk about another little field over in Kay County, which is about 5 miles to the west of the county line. And I picked these particular fields. They're very different. One is a thin upper Skinner sandstone field. Sandstone, well, it thickens up to as much as 30 feet, but most of the sandstone in there is thinner. And the other one is a very thick accumulation of sand in the Cleveland interval down at Cleveland Field. And then I have some, I think they're pretty, Burbank slides from a couple of areas in Burbank Field that I'll show you. And we'll kind of compare these. And I'm approaching this from how are clay minerals affecting what we see on wireline logs. And hopefully you'll get the idea of what I'm trying to convey. If not, ask me a question and perhaps I can explain it better. So we'll get started here. We're going to be looking at subtle reservoirs. When we drill oil and gas wells, as many of you here do, when we drill in these wells and we run our wireline logs, there are those reservoirs that have adequate porosity and permeability, resistivity because they contain oil and gas. They stand out, they're easy to identify, but there are a lot that don't. And I'm going to call this a subtle reservoir, and the Upper Skinner Reservoir that we're going to look at calculates really high water saturation, but produces oil and gas. So we're going to look at these fields, look at these reservoirs, and try to understand what's going on here, what's causing this to happen. And of course, the last thing on this slide, and I think this is very important, Hopefully, that what I show today, maybe it'll cause someone in here to go, hey, you know, we have that field out there, we have that well out there that's got that zone either behind pipe that, you know, the geologist said when they drilled that well, they had show in it, but it's you know, it's too low resistivity. We don't think it'll produce. Well, maybe it will. Maybe it deserves another look or reassessment. Okay, the study areas, I won't spend a lot of time on this, but we're going to look at this little field up here in Katy County, the Dobson Ranch Skinner Sandstone Unit. I'm going to show you a few slides from Burbank. Everybody knows where Burbank is. And then we're going to drop down to the Cleveland Field Unit, and I'm going to show you some of the work of my co-author, Connor Kane, who now works for Contango. He was working for Midcon Energy when he did this work, and is now over in Edmond with Contango. Now I'm going to jump over to this picture here on the right, and of course the red box is where the study area is. But in his talk, Nick mentioned plate tectonics and the collision of South America and Africa with Laurasia and the formation of these mountain ranges. And we don't think about this very much, but we have good evidence from zircon geochronology that the sand that we find in the Bartlesville, the Red Fork Burbank, the Skinner, some of the Cleveland, and let's see what else, what other zones have we done zircons on. These sand grains were coming from way over here in the northeastern part of the Appalachian Mountains during the Pennsylvania time. So those Appalachian Mountains during Pennsylvania were very high, and there were these rivers flowing westward, southwestward across what is now North America, bringing that sediment into the Oklahoma region and into the evolving basins that we had here. And Nick showed that slide of the Anadarko Basin, the cross-section through it. Those sediments were headed that direction. Same way most of the sediment in the United States, in the middle part of the United States, is headed down the Mississippi River into the Gulf of Mexico. But during the Pennsylvania time, the evolving Arkoma and Anadarko basins where the sediment sinks, and that's where the sediment was headed. And as a result, we have a great cover of sedimentary rocks in Oklahoma. They're thick in the basin. They're thin up here on the shelf and the platform where we are right now, but they're a tremendous host of oil and gas. And that's one reason the state has been has experienced such a significant part of its economic development, and in fact our lifestyle from the production of oil and gas. Okay, down in the Cleveland Field area, I'm going to show you this because it's a great story. In Cleveland Field, where you see this red circle, during Cleveland time, and here's this is a wireline log. It shows about 130 feet of Cleveland sandstone. There were two big channels flowing from the east. One was coming almost due east over by Collinsville, across Osage County, across Cleveland Field, and it just extends on over into Logan and southern Garfield County. At the same time, there was one coming down here from Kiefer, up through Jinx, across Cleveland, and then extended on west, and these two kind of merge out here and become difficult to separate. And Connor, in his thesis, mapped this area and showed how to distinguish between these two channels. Well, these two channels merge right over Cleveland Field, and as a result, you get over 100 feet of sandstone in that field. And we're going to look at that. And then we're going to also look at the Upper Skinner Sandstone, which is right down here at the base of this wireline log. And moving right along, well, here's a picture of Cleveland. Look at all those old wooden derricks. Here's downtown Cleveland. And look at the oil field that developed in that community. But data sources, okay, we're going to be looking at wireline logs from the Mid-Continent Geological Library, stuff from the Commission. Nick, at the time we looked at these Cleveland cores, they were in Mid-Con's shop. Now they're down at your shop. They're no pig now. But anyway, so I want to point out, if you're interested in what I present on the Cleveland field, look up Connor Kane's thesis at OSU. Mid-Con Energy contributed Petrobase production data. The Skinner data are from a variety of sources, including my work, and some early work done by a student in 1983, Carol Lojak. The methodology you're going to see is pretty much standard as we were out here exploring for oil and gas. And you're going to see structure maps that map the structure. Then started mapping the sand trends as they drape across these structures. Then started looking at the individual facies within the sand bodies where we have core, etc. Just like we would do if we're out here trying to explore for oil and gas. I have to talk a little bit about the clay minerals. And these are some thin section photomicrographs of sandstone. They're all Skinner. These are all Skinner pictures. And one of the clays we see that fills up the pore space is called kaolinite. And this is a quartz grain. This is kaolinite filling the pore. If you look at it under the SEM, it looks something like that. You see all these booklets, and you'll see there is space between these booklets. And water likes to get in there and hang out. And that water's hanging out in there, and when that electric log is run, that wireline log finds this conductive path. And as a result, if we have a lot of kaolinite in there, we may get a resistivity reading that is lower than the true resistivity of the fluids in the major pores. The other clay we see a lot of in the Skinner is illite. And this brown material you see around this pore and actually out in the pore, you can't see it probably, is illite. It looks like this in SEM, and it does the same thing. It creates this micropore system, water hangs out in there, and it cools the electric logs when we run logs across those intervals. I don't show pictures of chlorite. Chlorite's another clay. It's very common in the Red Fork Burbank and in the top of the Bartlesville. And then I'm going to show some pictures of some detrital clay, and I'll talk about detrital clay, talking about the accumulation of mud at the time these sediments were being deposited. And later on, you're going to see a lot of pictures of little bitty thin sand laminate or thin bedded sandstone with layers of clay or shale that separate the sandstone layer.
Pivoting on to the latest transfer portal buzz,
Well,
we've got
I'm going to talk about Burbank, and Burbank, when it was drilled, was anything but subtle.
Got away from it.
And I will show you, well, this is a picture of I think this is the Carter Oil Camp at Burbank. This is from the Oklahoma Historical Society. 1926, they're in the height of the development. Rick Fritz probably showed you a similar slide yesterday, but this is the Red Fork Burbank dispersal system. The sediment dispersal. The sediments originally come from northeastern Appalachian Basin. Some are locally generated down in here. And I'm not talking about the granite wash coming off the Wichita Mountains. But you have this fluvial deltaic system prograding southwestward towards the Anadarko Basin. And then out in the basin, we get some more Red Fork. We get some shallow marine sandstones. We get some basin floor fans. We have feeder channels coming into that, but Burbank's sitting right up here. And the neat thing about Burbank was we have this thick valley-filling channel, and it bends to the east. And when it bends to the east, it creates a trap where fluid migrating up through the Red Fork, Burbank sandstone, comes to this bend and tries to move up dip due to buoyancy, and it gets trapped in that bend. The great thing about that, it got trapped and it sat there for millions of years and separated. So in Burbank, you had a true oil and gas column over water. If you get down to some of these trends that are going more west to east or south to north, there's still oil migrating in those systems, but it didn't trap and didn't separate due to buoyancy. So you get those oil-water mixed systems that if you want to move a lot of water, you can mine that water, you can extract the oil. So let's look at Burbank. All of the slides that I show that have gamma rays, you're going to see that whenever we have these, what we call hot shales or core shales, use Phil Heckel's nomenclature, these represent inundation of the shelf, rapid transgression, rapid flooding, stratification of the water, and these are uranium-rich markers that just show that the area flooded at some time when that ice down in Gondwana and around the southern hemisphere towards present Antarctica melted and sea level rose. So each of these represents a rapid rise in sea level. Well, they're great markers, and you can pick them off the gamma ray curves. And we use these markers because they are so widespread to separate our stratigraphic units. So I always identify those, and we're going to see the mineral coal marker in here, and the pink marker is not shown on this log. And here's our Burbank sandstone sitting down here. This is the 20% porosity line. Even if we correct this back 2%, it still has about 22% porosity. That's just tremendous rock, and that's the reason we had those high flow rates in the early development of the Burbank field. So this is just a little snapshot down near the town of Burbank of isopotential of cable tool drilled wells. Data reported prior to shooting with nitroglycerin. And you can notice these are impressive. This red is from 2,000 to 4,000 barrels of oil per day naturally floating in those wells. And yellow is 1,000 to 2,000. But this was a study that was done a number of years ago when we were evaluating the effect of fracturing on oil and gas production rates in Burbank. If we look at the thickness of the Burbank sandstone in the same area, if it's red, there's greater than 75 feet of sandstone that was drilled. And this is over in that Stanley Stringer, and here's the main part of the field over here. So there's just a tremendous reservoir. This is not a subtle reservoir. This is a great reservoir. It produced, after drilling, didn't require fracking. And a short cross-section here, and I think that cross-section sitting right down in this part. So many of these wells were drilled so long ago, they don't have modern logs on them, so it's hard to find modern logs. But high porosity, top of the Burbank sandstone, again, those markers that we use to establish where we are in the stratigraphic interval. And this is just to show you how this sandstone can be incredibly thick and then rapidly thin. And in the area here between the main field and the Stanley Stringer, there's no active fill or sandstone at all. Let's jump up to the Shiver area, and we'll do the thickness first. And again, greater than 75 feet is shown in red. We have these really nice thick trends. Probably additional. I have hypotheses to explain these, which we won't go into. But these are stacked channel fills within this valley, and this is one of the late stage valley filling channels. But look at some of these initial potentials. There is one brown well right there, and a brown is greater than 4,000 barrels of oil per day. So it's important to remember that these wells were flowing before shooting. And usually on the completion records at that time, they would give you a flow rate prior to shooting the well and then a one after shooting the well. So this is our best guess at what the natural flow is from this reservoir. Now, to the south, down several miles to the south, we have that Little Chief area. And the Little Chief area was not developed until the 50s and the 60s when new technology came along, sand fracking. They didn't need sand fracking to produce the main part of the field, but that area down to the south was a little less permeable. But the new technology opened it up. So that's what we have to keep in mind. How is new technology going to help us get more oil and gas out of these reservoirs? Okay, let's jump up to right up here in eastern Kay County. We're going to look at the Upper Skinner Sandstone that sits down there. This is a Dobson Ranch Skinner Sandstone unit. And this is a modern log. Perforations are shown. And you can see that this sandstone only has 2.5 ohm meters resistivity. It has pretty good indication of perm by microlog. And it has mud cake indicating it has permeability. But the porosity in here, and this is run on a 271, so let's correct it back. It's going to average something about 15% porosity in there, but just quite a bit less than what we were seeing in the top of that Burbank sandstone. But this little field, and yes, we'll start with the structure map. Here's the Osage County, Kay County line. Here's one of those kind of north, east-west, north-northwest, east-southeast trending faults through there. This fault is placed on the map solely on subsurface data. Some minor faults, and these are some minor little faults in here on the top of the Mississippi. And I haven't looked at seismic in this particular area, but some of the seismic to the south of here, at top of that Mississippian surface is really irregular. So there were some things going on there that either faulting or karsting that affected that surface. But we're going to be looking at this little field that sits right over here on the edge of the mapping area. And let's look at the thickness of the sandstone. These contours are 20 feet, and here's one little channel that sits over here. I bend it back to the west towards a well with thin sandstone that sits up here. It might continue on over into Osage County. Certainly don't have the data to put it there. But, you know, if I were selling this deal and I owned the acreage here, I could always bend it that way to sell the deal. But I'm not interested in that area. I'm interested in this area over here to the west, where we have greater than 20 feet of sandstone, 27 feet, 34 feet. There's the thickest one right there. But most of these are 10 to 20 feet in thickness. And when we look at these in the cross section, across this channel, it looks like this. Here's the base of our channel, eroded into the underlying shale. Here's our mineral coal marker down below. It's absent over here to the east. It's almost gone on the west side. But what I want to point out are these water saturations. This particular well has a water saturation of 0.75 or 75%. The one to the east has a 69% water saturation, porosity of 13%, porosity of 15% to the west. But when they completed these wells, and the one on the left was not fracked, it was acidized, it produced 25 barrel oil per day to 5 barrel water per day, which is a pretty high ratio oil to water number considering what the water saturation is. And all of the wells in this field have this low resistivity, and we are attributing that to clay minerals, autogenic clays in between the sand grains that are fooling these wireline logs. Now, how did they know to complete this? Well, I give Dave Brierly the credit because he was well site geologist on one of the more recently drilled wells. Some of the early wells drilled in here drilled right through it and didn't complete it. But I'll bet Dave saw a good show in those samples and he convinced them to complete the well. And they drilled a bunch of wells in here. So we know it was economic. And it's now a unit, not producing very much at present, but at the time, it's a good little oil field. Okay, let's jump down to Cleveland. Okay, I have plenty of time. Anybody is still awake out there, I'm going to talk about Cleveland Field. Okay, let's go down and look at these channels where they cross the structure. This is probably, I don't know, this may be the most important slide for most of you in here. It goes back to 1904 when the field was discovered. They're producing daily oil productions, 10,000 barrels a day out of Cleveland and Bartlesville sands. Here's in 1950s and 60s, we got it back up over close to 2,500 barrels a day when they were flooding the Bartlesville sandstone. And then here's the Cleveland redevelopment, and in 2015, this field was up over 700 barrels of oil per day. Cleveland Field, maximum depth on these wells is about 1,700 feet. It's a lot of oil from 1,700 feet. Now, the Cleveland sandstone was the first discovered. It was high gas-oil ratio. Matter of fact, there was a gas cap on the field. So what they do, they vented it and blew it off. And then went to the Bartlesville, because the Bartlesville was oily. They couldn't do anything with that gas at the time. So we're going to look at, this is an old core analysis from 1962. That's old. That is old now. Yeah. Wow, I wouldn't have thought that 40 years ago, but so this is the upper part of that Cleveland. This was the old part that was originally completed that was gas rich. Then you'll see you have it's over 25 ohm meters. Here you see 15 ohm meter zone finally tapering off into a less than 5 ohm meter zone. What's important are oil and gas shows across this entire section of rock. And if you look at the core data, average perm down here is only 2 millidarcies. It goes to 4 up in this interval and gets up over 53 millidarcies. And there's some over 100 millidarcy rock in here. There's some really sweet rock in the upper part of this Cleveland interval. But this part of the rock was ignored. It was bypassed. They tried this. It was so gassy. They said, this is not making us any money. I don't know if they tried this, but they knew they had Bartlesville sitting down below, because who's going to mess with the Cleveland when you have the Bartlesville oil? So a cross-section through part of the field, again, thanks to Connor's work. You can see the top of the Cleveland sandstone. You can see the kind of delineated that high permeability zone. This is permeability. This is 300 millidarcy line here. This one, this is a 100 millidarcy, 300 millidarcy, 300, and then this one has a 200 millidarcy line. Well, this was what the original field was completed in and produced a short time. Then MidCon came in and started producing this lower permeability rock below. And what's that rock look like? Well, I'm going to show you a bunch of rocks, but okay. So detrital clay laminate accumulating here between fine grained sand and silt. Probably not going to be reservoir. And then of course we have background, what we would call claystone or shale in this case if it's fissile. That's our background rock. Here's one that will make the log crazy. When you get sandstone with these laminate touch or touch each other connected, there's still oil and gas in the sand between the clay, but there's no permeability across here, or very little permeability. Here's another one that has horizontal laminate, and this is a really good rock. Sure, there are clay particles and material accumulated along these horizontal laminates, but it has good porosity and good permeability. You can see the difference here, I hope. You can see that this is coarser grained than this massive sandstone. This cross-bedded sandstone is telling us you have a fluvial system that has enough current. You're building these foresets, moving that sand along, and then you have this massive sandstone. How's that thing forming? Well, maybe the sand is coming into a lower energy condition. We're not getting cross stratification. Almost always, this rock is better rock than that rock. And here's one that really throws the logs for a loop. You have these streams ripping up the bottom of the channel, or ripping the sides of the channel are collapsing, and you get all these clay clasts that accumulate at the base of these flow units. And the wireline log over here, it sees this as shale. Well, it's not very good rock with porosity and permeability, but it fools the log. And here's another one that fools the logs when you have enough of these isolated clay clasts, shale clasts in the sandstone. So let's look at a modern log, and this one has a really, really interesting story. Modern log in the middle of that old field. Here's that upper high permeability zone, which they did go ahead and perforate when they completed this well. But the interesting thing about this log, they put water back in this gas cap when they originally tried to flood the Cleveland, tried to fill that gas cap with water. As a result of that secondary recovery and blowing off that gas cap, now you have lower resistivity sitting over higher resistivity in one of those lower permeability zones. And then that resistivity continues to drop off as you go deeper. Permeability, according to the micro-resistivity log, is good across all these zones. You can see the difference in permeability by core plug and mini perm over here on the right. This bottom zone calculates 47% water saturation. This zone is 28% water saturation, and the old gas cap's 54% water saturation. And the recent coring reflected that. This upper part was almost absent of show. Had good oil and gas shows in here down into the tighter rock. So they completed this rock. And here's a snapshot of production rates from 2018 or 17. This biggest bubble is 104 barrels a day. The well I just showed you the log of is 48 barrels of oil per day. And the entire field was 107, it's over 700 barrels of oil per day. This structure map is on the checkerboard limestone for those of you who are familiar with stratigraphy in there. But it's just a great example of how going in and reevaluating an old field that had been on production since 1904, and they did this work in the 2000s, and they were able to rejuvenate an old producing area. So, all right, we have to end sometime, so might as well do it now. Based on our work looking at sandstones, we know that orthogenic clays in the pore space can cause these sandstones to calculate high water saturation. We know that a combination of those, and especially interbedded or interlaminated clay class, interlaminated wispy clay in the sandstone can really reduce permeability, even though the sandstone can be oil saturated. We didn't have any core up in this Dobson Ranch Skinner unit, but we believe, based on what we see there and what we've seen in other upper Skinner fields down in Payne County, that this is probably an orthogenic clay issue that causes those wells to calculate high water saturation. In Cleveland Field, The people that drilled Cleveland were lucky enough to get 2 of those big channels crossing that structure, that anticline. And the high permeability gas cap in Cleveland Field was blown off as people moved to produce the well out in Bartlesville. But we know that using modern wireline logs and going in and fracking those lower permeability zones that are deeper, yeah, you produce water with them, but you're also able to produce a lot of well. And we just hope that, these are just 2 examples where several zones were either bypassed or were difficult to evaluate, and we're always out there looking for more. And I know I am, and I hope that someone will be doing that here in the Osage as well. So that's it. Thank you. I welcome any questions.